In this video, we'll take a look at compositions of functions. So we can compose functions or combine functions in using algebraic operations. So that's our first outcome. You can take functions and add them together. So f of g of x is equal to f of x plus g of x, just so you can get to the used to the notation. We can take the difference of two functions, the product of two functions, and the quotient of two functions. So let's take a look at an example. So if we have f of x equal to x minus 5 and g of x equal to x squared minus 1, f plus g of x means to take our two functions and add them together. So we take the function x minus 5 and add to it the function x squared minus 1. Add like terms, we end up with x squared plus x minus 6. So that's our new function, f plus g of x. Next, we can subtract functions. F minus g of x means take the function f of x and subtract the function g of x. The function f of x is x minus 5. What to be careful with here is when you subtract the second function, make sure you include parentheses, because we're going to distribute the negative through both terms. We end up with x minus 5, distribute the negative, minus x squared plus 1. So when we add like terms, f minus g of x is equal to negative x squared plus x. Negative 5 plus 1 is minus 4. Third thing we can do with functions is we can multiply them together. F times g of x means take your function f, x minus 5, and multiply it by function g, which is x squared minus 1. Use the distributive property, or FOIL. We take x times the entire second function, so x times x squared would be x to the third. X times negative 1 is minus x. Then we take negative 5 times both terms. Negative 5 times x squared is negative 5x squared. Negative 5 times negative 1 is plus 5. So our function f times g of x, let's see, we don't have any like terms, but we want to go ahead and put these in descending order. So we start with x to the third, minus 5x squared, minus x, plus 5. The last thing we can do with functions is we can divide. So d, the function f divided by g, we would take our function f, x minus 5, and divide it by the function x squared minus 1. This doesn't simplify. If we were to factor out the denominator, we still wouldn't have any common terms. So f divided by g of x is equal to x minus 5 over x squared minus 1. So something to notice, the domain of each of these functions, the two original functions have a domain of all real numbers because they are a line and a parabola or a quadratic. So when you combine them by adding, subtracting, or multiplying, we also have a domain of all real numbers. But when you divide the two functions, we end up with a rational function. So in this function, the domain is restricted. So just a quick review of domain. The denominator of a function, a rational function, can't be 0. So the domain of this function would be all x values, except those that make the denominator 0. So if we take x squared minus 1 and set it equal to 0, we get x squared equals 1. Square root both sides, we get plus and a minus 1. So x is all real numbers except for 1 and negative 1. If you were to write this in interval notation, it would be negative infinity to negative 1, along with negative 1 to 1, along with 1 to infinity. All right, so our first objective, we can combine functions using algebra. The next part is a composition of functions. So a composition of functions is when we take the output of one function and use it as the input of another. we call the entire operation a composition of functions. So for any input x and functions f and g, this action defines a composition, f with a little circle composed with g. That means f of g of x. And another way to write it is take the function f and substitute inside of it all of g of x. Then, as we talk through, we're going to look at the domain of the composite function, and then also take a look at f composed with g and g composed with f to see if they're the same. So first thing we're going to do is evaluate composite functions using just a table and a graph. So the first example, make this a little smaller. The table of values, we have an x value, then we have f of x. So these would be all the y values associated with the function f. Then we have a function g of x. These are all the y values associated with the function g. So when we take a look at the notation, f of g of 4, that means take and substitute inside the function f whatever g of 4 is. So find your x value 4. G of 4 is the y value. So when x is 4, g of 4 is negative 3. So we're going to take the answer, g of 4 equals negative 3, and find that. So we're taking the output of the function g and letting it be the input of function f. So what we want is now is f of negative 3. So find negative 3 as your x value, and look at the function f output, which would be negative 3. So f of g of 4 is equal to negative 3. The second, if we find g of f of negative 5, find f of negative 5 first. So that means when x is equal to negative 5, what is the output? The input of negative 5 gives us an output in the function f of negative 2. Now we're going to take the output, negative 2, and put it in the function g. So that means I'm taking g of negative 2. So find your x value, negative 2, and in the function g, the output is 0. So g of f of negative 5 is 0. All right, so what happens? Notice the next two is f composed with itself, g composed with itself. This says f of negative 1. So f of negative 1, when x is negative 1, the function f output is negative 5. So f of negative 1 is negative 5. Now we take negative 5 and find the output of function f. So when x is negative 5, the output is 2. So we end up with 2. And part D, g of negative 4. Find g of negative 4. So when x is negative 4, the output is 5. Now take the output 5 and put it back in the function g. So when x is 5, the output g is 1. All right, so we can also evaluate composition of functions on a graph. If we use the graphs below, f of x and g of x, to evaluate the expressions, write your answer as an integer or a reduced fraction. So the function f is some crazy function in the first graph. The function g is a linear function in the second graph. So our first problem is to find f of g of negative 1. So we find g of negative 1 first. That means when x is negative 1, what's the y value in function g? So we're working with function g. When x is negative 1, the y value is 2. Now we're going to take f, the output, 2, and put it in the function f as the input. So now we go to the function f. When x is 2, the y coordinate is negative 3. So f of g of negative 1 is negative 3. The second problem, we want to find g of f of negative 4. We find f of negative 4 first. So on the function f, that's this first function, when x is negative 4, what is the y value that goes with it? What's the output? The output is negative 2. Now we're going to take that output and put it inside the function g. So when x is negative 2 in the function g, we want the y value that goes with it, which is 3. Okay, well, you're probably more familiar if you've done compositions before with composition of functions as an equation. So now our outcome, we're going to create a new function by composing two functions together. We're given that f of x is equal to 5x plus 6, and g of x is 2x squared minus x minus 1. Again, we have a linear function and a quadratic. This time we're going to do a composition of functions. A, the notation f combined with g of x, means in the function f, substitute the function g of x. So our function f is 5 times something plus 6. And what we're going to substitute in there is the entire function g of x. So we're taking f of 2x squared minus x minus 1 and substituting that in our function f. So 5 times 2x squared minus x minus 1 plus 6. Then do the arithmetic, multiply through, or the algebra, multiply 5 through. We get 10x squared minus 5x minus 5 plus 6. Add like terms, we get 10x squared minus 5x plus 1. So that is the function f composed with g of x. So we're taking a function, the output, which is the formula, and putting it inside the other function. All right, so part B, take the other direction, g composed with f of x. So that means in the function g, substitute the formula f of x, that 5x plus 6. So the function g is 2 times whatever x is squared minus x minus 1. We're going to substitute, let me put parentheses here, we're going to substitute the entire function f wherever their parentheses are. So we get 2 times 5x plus 6 squared minus, use parentheses, 5x plus 6 minus 1. Now we're going to do the algebra and add like terms. So we end up with 2 times, when you multiply 5x plus 6 times itself, we end up with 25x squared. Don't forget the middle term. 5 times 6 is 30, double it. That's plus 60x. And then 6 squared is plus 36. Minus 5x minus 6 minus 1, because we distribute the negative. Multiply through by 2, we end up with 50x squared plus 120x plus 72 minus 5x minus 6 minus 1 is negative 7. Add like terms one more time. 50x squared, let's see, 120x minus 5 is plus 115x. 72 minus 7 is plus 65. So this is g composed with f of x. So notice, it matters. If you take f composed with g, you get a different answer than g composed with f. We get two different answers. So they're not commutative. It doesn't work to combine either direction. You'll get a different answer. All right, part C says find f composed with g of negative 1. Well, in part A, we found the function f composed of g, so now we can take negative 1 and substitute it in our function. So we get 10 times negative 1 squared minus 5 times negative 1 plus 1. Let's see, that would give us positive 10 plus 5 plus 1, which is 16. So f composed with g of negative 1 is equal to 16. All right, next part that we're going to take a look at is how you find the domain of a composite function. So in this problem, we're going to take f composed with g, and then we're going to talk about the domain. So f composed with g, notice these two functions are not, the domain of each of these is not all real numbers, okay? So keep that in mind. When we take the compositions of functions, f composed with g of x, that means we're going to take the function g of x, which is 1 over x, and substitute it in our function, 4 over x plus 2. We're replacing x with 1 over x plus 2. So this is a complex fraction. To simplify this, if you haven't simplified these before, what you can do, we have a fraction within a fraction. The common denominator is x. So what you can do is, to simplify pretty quickly, multiply the numerator and denominator by the common denominator of all the individual fractions in your complex fraction. What we end up with, 4 times x in the numerator is 4x. The denominator, we get 1 over x times x, which is 1, plus 2 times x, which is 2x. So our composition of functions is 4x over 1 plus 2x. Now we want to find the domain. So we can find the domain of the function that we just created, but we also have to look at the function g of x that we put inside. So how do you figure out domain? So I've got a checklist. So the following values have to be excluded from your composition. If x is not in the domain of g, it can't be in the domain of f composed with g. So let's see, what's the domain of just g? The domain of the function g is all numbers except x can't equal 0, because that's what makes the denominator 0 and undefined. Then you take a look at the function you just created, the 4x over 1 plus 2x. Find the domain of your composition. So the domain of the composition, it excludes 1 plus 2x. The denominator can't be 0. So if I subtract 1 from each side, divide both sides by 2, then x also can't equal negative 1/2. So the domain is all numbers except 0 and negative 1/2. So the way we would write that is in interval notation, negative infinity to negative 1/2, union, negative 1/2 to 0. You have to go in order from low to high, union, 0 to infinity. All right, so now we've taken a look at composites and the domain of composite functions. Let's try the domain one more time. This time let's use a square root function. So we're going to find the composite function first, f composed with g, and then we're going to figure out the domain. So f composed with g of x means take the function g, which is x squared minus x, and substitute it into the function f. So I have square root of 56 minus x, and x we're going to substitute the entire function, x squared minus x. If we multiply through, we're going to end up with the square root of 56 minus x squared plus x. That's f composed with g of x. And then we can take that and put it in descending order. So you can also write that as the square root of negative x squared plus x plus 56. Okay? Now the domain, you take a look at the domain of g of x, the function that you're putting inside the other function. The domain of g of x is all real numbers. There is no limitation. So we don't have an additional limitation on the domain. Then you take a look at the domain of the function that you just created. The function we created is a square root function. That means underneath the radical, we have to have that be greater than or equal to 0. So set your negative x squared plus x plus 56 greater than or equal to 0. So we're going to factor and solve, multiply through by a negative. I end up with x squared minus x minus 56. And when you multiply through by a negative, the inequality changes direction. Factor. I get, let's see, two numbers whose product is 56 and sum is -1. Then you want to make sure, let's see, the larger number needs to be negative. 7 times 8 is 56, so that's going to be -8 plus 7. So I'm going to set it equal to 0 for now, and I get two answers, x equals 8 and x equals -7. So how do I know x equals -7, x equals 8? So how do I know which one of those? It cuts your number line into 3 intervals. So which of these are going to work inside here? Okay, so check a value between -7 and 8, let's say 0, and substitute it inside your square root function. So that would be 56 minus 0 plus 0. The square 56 is positive. We can take the square root of that. That's in your domain, so this entire interval is in the domain. Then check and see anything less than -7, if you substitute it in here, you're going to get a negative number. Anything greater than 8, if you substitute, you're going to get a negative number. So our domain are the values between and including -7 and 8. All right, last idea in this section is how to decompose a composite function into its components. This is something you'll have to do in calculus when you learn the chain rule. So an example, write f of x equals the square root of 5 minus x squared as the composition of two functions. So what two functions could you select, g and h, so that f of x is the composition g composed with h? So to do this, you look for a function inside of a function. As a possibility, you notice that 5 minus x squared is in the inside of a square root. So we could decompose the function as let h equal 5 minus x squared and g equal the square root of x. So notice square root of x, there's a square root function, and then there's an expression on the inside. So if you let h equal 5 minus x squared and g equal square root of x, then the composition of those two ends up being your original function. So the solution, your two functions, could be 5 minus x squared and the square root of x. Okay, another option, if you let h of x equal x squared and g of x equal 5 minus x, that would work as well. But try to find one where you have something like the square root of x and then something, the entire expression on the inside. So let's take a look at one of these examples. So if our f of g of x is 1 over x minus 9 to the 5th, find two non-trivial functions, f and g, so that when you take the composition, you end up with this. So here's the hint. We have an x minus 9 to the power of 5. Let one of your functions be x minus 9. The g of x is going to be x minus 9. And then f of x is going to equal 1 over x to the 5th. So if you take the composition f of g of x, you're going to end up taking 1 over x minus 9 to the 5th.